All right. So as we've mentioned before, these we've had two classes that are going simultaneously through this, and a lot of the folks decide to just join after the fact, watching the videos. But I did just send out a note to the group in Coolville and Amesville, and saying because so many of them have sort of lagged behind, we're inviting anyone from that group to come to Marietta in not this coming weekend, but the weekend after to do the labs and the exam. So the labs and exam, just to recap how that works, you'll come to 620, 622 8th Street in Marietta. I'll send you some more specific directions here before the event, but 622 8th Street. We'll meet here that we're going to do the labs next door at 620. Where the building that we're setting up as our training center is available for use, but it's a little more comfortable than what Jess is dealing with at the moment. At least it's indoors, but it's unfinished. So it's just a big room. We'll set up our tables in there. We'll do the labs there, but we'll do the review and any of our get acquainted type stuff. We'll do that here in 622. So there's plenty of space, and we'll set up the tables and the chairs for the exam. So we'll be indoors and comfortable. But just to let you know, we'll go bounce back and forth between the two. We'll start on Saturday at 8 a.m. I usually do a bit of a orientation, takes about an hour. So if you're traveling in and you're running late, don't worry about it. You know, if you're an hour late or so, you're just missing all the great discussion that I'll be leading. But obviously, if you can be here at 8, that's the best. And
Way over there and way back
so,
here.
Rich, I hear some people back there. I'm gonna mute you unless you have something to say. Then you'll unmute yourself there. All right. So, okay. So we'll meet at 8 o'clock, and then Saturday, and let me give you the specific date so I'm not Saturday the 22nd. We'll go ahead and I lost my visual screen here. Um, oh, there we go. Yeah, we'll meet um, for the labs, and that's going to take us all day. So it'll take us from about 8 in the morning until 4:30, depending on how quickly people do it. But all of those hands-on labs will walk through all of the tasks that are required as far as the ETA certification is required. But I think you'll also find it helpful to actually work with systems, because you're going to put together a string inverter system, you'll put together a microinverter system, a power optimizer system. We'll hook batteries together in series and parallel. We'll do a shading analysis with the Solar Pathfinder. So there are 16 different labs. We'll put together a solar generator, and you'll go through all of them. At the end of the day, then when you're done, free to go. You know, obviously, and then we'll meet back the next day, Sunday, at 8 a.m. So we'll spend about 3 or 4 hours. Oh, and I will serve lunch that day. Well, if you don't like pizza, bring your own. But we'll bring in some pizzas there, and we'll have coffee available and that kind of thing. Um, you don't need to bring anything except just be comfortable, wear comfortable clothing, and be prepared. Bring a good mood, and then we will on Sunday we'll do a review. So we'll walk through, we'll review the thing. It's a good opportunity for you to ask questions if there are things that you're not quite sure about. Typically, we'll break for lunch, and then we take the exam. Or you may determine that you want to just plow straight on through and take the exam right away in case you've got flights to catch or something like that. You have 2 hours to take the exam. It's 75 questions, multiple choice, very similar in format to the questions at the end of each chapter. And I think, to my way of thinking, they're not as hard because some of my questions in the book are designed to catch you up a little bit. Sometimes I try and make you miss it, not make you, but I give you the opportunity to get it wrong because I think you learn better if you screw things up, and then you'll remember it better. But the exam is not designed to be tricky. It's not designed to try and fool you with anything. They don't use negative questions. It's all, I do a lot of which of the following is not, and then you have to pick the one that's not. Sometimes your brain doesn't see the word not, so you pick one that is. Theirs are all going to be in the positive. So that's kind of it. Then when you're done, I'm hoping, I'm not 100% sure because I don't have the product here yet. My goal is after we're done with the test, those people who want to stay will do a small install. So we'll install 4 or 5 solar panels on our solar array here at this facility. So it'll be a rooftop on top of a small garage. We'll install the racking system. We'll install the microinverters. We'll hook it up. So if you want some practical, real world, it'll probably take us 2 hours or so. We'll just do that install. So that's kind of a nice way to just finish out the day, get a sense of it, how that system works. One time when we're doing the labs, we will take a moment to take a look at the installed system. So we'll walk through everything, all the components. I can show you how everything goes together. So you'll see a real world install that's working and operating. And that may give you a better feel for how these things go together if everything here is new to you. Okay, so anybody have any questions on that, on the 22nd and 23rd, what we're about?
Are you gonna write down and send out like where we're at, which day, what time, and like send that out before we go?
Yeah, I'll send a note. Yeah. I'll send it saying 8 o'clock here till 4, and then we'll have the, and we'll do the, we'll send out a full schedule before. But if I give you too far ahead, everybody just loses track. So, so that's the plan. Okay. So, so that's the goal for that weekend. Any questions? What's that? Let's see. Is that ISO Rich? Did you have a question? You're not coming through clear. Oh, I think it's somebody in the background must be talking because your lips aren't moving, but I hear somebody. All right. Okay. So if anybody has any questions, fine. Just interrupt me as we go. But at this moment, you should be on chapter 8 or 9, 8 and 9 within the book. And hopefully everybody's been following through on the understanding photovoltaic. And so chapter 8 is all about wiring. So that's, let's see, I'm going to, can everybody hear? Because I just saw a note there from Rich saying he couldn't hear. Can everybody hear me?
Yeah. Oh, yeah. Mm-hmm.
Okay. All right. I'm going to hit mute on yours because I'm getting some background noise. Okay. So let's talk a little bit about wiring. And so I'm going to share the board here. Chapter 8 is all about wiring and wiring size. So let me see if I've got... Will this work? Yeah. Okay, so let me find my whiteboard. All right, so you should see the whiteboard here. And when we talk about wiring systems, we're going to talk about the different circuits. So I'm going to use this as a traditional string inverter system. And so this is the array. And from the array, we're going to connect into a combiner box. Now, the only difference between a combiner box and a junction box is that in a combiner box, we make a parallel connection. In a junction box, think of it as just a glorified wire nut. We're just transitioning from one type of cable to another. So from the combiner box, we come and typically you're going to connect into a DC disconnect. And that DC disconnect is very often integrated into the inverter. So the inverter is there. And then from the inverter, we go to an AC disconnect. And that AC disconnect has to be located within 10 feet of the electrical meter, externally operable, well marked, lockable. So all of that, this is considered the main shutoff of the solar system. So the reason it has to be there near the electric meter is if you get a first responder or somebody like that coming to your home, your house is on fire. It could be the utilities coming as well. But let's say your house is on fire. One of the first things they're going to do is want to disconnect that building from the electric grid. So traditionally, they've just pulled the meter like it's a fuse. And as soon as you pop that meter, you've disconnected the structure from the grid. One of the downsides of doing it that way is it can arc. It can like pulling a fuse when it's under load. So now the NEC requires that you put a utility disconnect switch right there at the meter. So they don't have to pull the meter anymore. They can just flip that breaker and now you're disconnected from the grid. So from the AC disconnect, you're going to go into the service panel. This would be a load side connection. Here's the main, and the main would go out here, I guess, to the utility disconnect. And from the utility disconnect, it's going to the transformer up there on a pole, and that's a system. So everybody, hopefully, this is not new to anybody. So now there are different circuits involved in this, and we call the portion between the array and the combiner box or the junction box, we call that the PV source circuit. And I'm just giving you these references because people will refer to these things and you need to know what part of the system they're talking about. Now, from the combiner or the junction box, and these are used interchangeably depending on whether you're making a parallel connection or not, then this circuit is known as the PV output circuit. And then from the DC disconnect to the inverter is the inverter input. Now, the way I've drawn this, the inverter input is already pre-wired. It's built into this unit, but it doesn't have to be built into that unit. You might have a separate disconnect from the inverter, and there might be 10 feet or so between them. Now, the DC disconnect has to be located within 10 feet of the inverter. The thing is shutting off. And then the AC portion of this system is known as the inverter output. Okay, so those are the major systems of a string inverter system. Okay, so how do we size the wire here? And I think, did I go over some of this last week? I'm trying to remember as far as classes, because I do this stuff a lot. So if I did, I apologize. This may be a little bit of review, but let's assume this is a ground-mounted system, so it's not up on a roof. And we look at the service panel, and the panel has an ISC of, let's say, 9.6 amps, an IMP, 9.3 amps. It's always going to be less. A VMP of, let's just say 27 volts, and a VOC of 30 volts. Just making these numbers up, but they're going to be somewhere in there. Okay, so how do we size the wire? Well, the wire is always sized based on amps. Amps is current, and we want to take the worst case scenario. So let's use the ISC. So we take the ISC. So each panel has 9.6 amps. And the National Electrical Code says we have to always multiply times 1.25. So 1.25 is just our standard headroom. You don't want to have, you need wire that's capable of taking whatever amps you're putting through it and having a little bit more capacity. So what would happen if we had strings of 10? So let's say we have 3 strings of 10. Well, I've got 10 panels hooked together in a string. When I hook them together in series, which is a string, volts increase, but amps remain the same. So whatever is the amps of one panel is the amps for the whole string. So I'm going to go 9.6 times 1.25, and that gives me 1.25 equals 12. So 12 amps. But because this is solar, and solar can be variable, we are required, until we hit the first piece of electronics, to multiply it times another 1.25. So I take that times 1.25, and now it's 15 amps. All right, so we need to have wire capable of handling 15 amps here. So if you look up in your book, and I think it's page 111, if I remember right. And on page 111, yep, it's page 111, there's a table that has the maximum ampacities of different sized wire. So if you're looking at that on page 111, we read from the furthest left column. That gives us the size of the wire. And then the second column is low temperature wire. So we're always going to size our wire based on the worst wire that we could use as far as ampacity. So we're going to draw it from that first column. Even if we're using high temperature wire, even if we're using like PV wire, which would be in column 3 there, or column 4, the 90-degree wire, it has a higher rated ampacity, but we don't use that. We don't use that because your circuit, let's say we're going from here to here. Well, there's a connection point here where the wire is connected to, a little lug in there, and there's a lug in here. And those have temperature ratings the same as the wire does. I don't necessarily know what the temperature rating is of that connection point. So if I were to say, okay, my wire is rated for 90 degrees, I don't know if these are rated for 90 degrees. The worst case is they're rated for 60 degrees. And it doesn't matter if this is all rated for 90 degrees. If I have one part of that circuit that's only rated for 60, I have to go with the lowest. Otherwise, that's going to become the weak point, and it's going to be the part that bursts into flames. So I go with the worst case. Since we don't know what they are, and maybe that equipment will change out, let's just always use the first column. Let's always use 60 degrees Celsius when we're sizing this. So when I know that I need 15, well, I could get by with 14 gauge wire. But the wire that's connected to the panels in today's market is 12 gauge wire. 12 gauge wire is rated for 20 amps. Well, I only need 15. It's rated for 20, so we're fine. So I know that these wires here, because they came with the panel, are going to be 12 gauge. And they're rated for 20 amps. So it exceeds, so that's fine. Now, let's say there's a breaker in here that I want to connect to. 3 breakers. What size breaker do I use when I connect in? Well, you round up to the next commercially available breaker. Well, this happens to be 15 amps, so I can use a 15 amp breaker. So I could use 15 amps. If it turned out it was 15.5 amps or whatever, I'd have to use 20 amp breakers because you round up to the next available. So in this case, I'm going to use 15 amp breakers. Now, what is the current that's going through this wire if I make if I make a parallel connection in here? Well, when we make a parallel connection, the voltage stays the same, but the amps increase. Well, we've already determined that the amps are 15 amps. So now 15 times 3, the wire I use here has to be capable of carrying 45 amps. So I look in my table, and 8-gauge wire can carry 40 amps. 6-gauge wire can carry 55 amps. All right, so I'm going to use 6-gauge wire. Can't use 8 because it's too little. So I'm going to use 6-gauge wire. Now, if there's a breaker here or a breaker or a fuse in my DC disconnect, what size fuse or breaker do I use? Well, I take 45 and I round it up to the next available commercial size, which in this case I think is a 50 amp breaker. I don't think they make 45 amp breakers. They might, but I don't think they do. So if they do make 45 amps, I could use a 45 amp. All right, as long as this 50 amp breaker does not exceed the capacity of the wire. Well, the wire is 55 amps, so I'm good. Because you don't want to have a breaker that's greater than the capacity of the wire it's connected to. It can be equal to it, but it can't be greater than. All right, everybody understand how we've sized the wire to this point?
Mm-hmm.
Okay, so now what happens in the inverter? Well, we transition from DC to AC. So if I said that using these, it was going to be 27 volts times 10. So it was 270 volts each string. And it was in reality 9.3 amps. So how many watts is our solar array? 270 times 9.3. It's basically a 2,500 watt solar array based on just what I've pulled out of the air here. All right, so it's a 2,500 watt. So let's say that I've got a 2 kW inverter. Why would I have a 2 kW inverter and a 2,500 watt solar array? Well, it's that phenomenon that's known as clipping. Okay, and if we wanted to know what's the inverter load ratio, it would be 2.5 divided by 2. And my guess is that's 1.25 divided by 2. Yeah, 1.25. So this would have a 1.25 inverter load ratio. So that's fine. That's normal. We see about a 1.3. That's normal today. Could I put a 3 kW inverter there? Yeah, no problem. It's just that I might oversize my system. I might pay more money than I needed to. So we find that at about a 1.3 inverter load ratio, you get the best economic return for your investment. But that's all it is. Now your inverter has a minimum. So I couldn't put like a 1 kW inverter because this would overwhelm it. But if you look at this system, it's going to say you can handle anything from, let's say, 1 kW to 3 kW. That might be its operating range. So that'll be fine. All right, so let's say we've got a 2 kW inverter. What does that tell me? It tells me enough to know how I size this wire. So what's going to be the amperage? What's the output in amps? Well, 2,000 watts. And we know that it's going to be putting out 240 volts because it's a grid-tied system. and this is America, so it's going to be 240 volts. So I say 2,000 watts divided by 240, and that gives me 8.3 amps. Okay, everybody see that? So the output is going to be 8.3, but because the National Electrical Code says I've got to multiply everything by 1.25, I multiply that times 1.25, that's my safety margin, and now I get a 10.42 amps. All right, so my wire here needs to be able to handle 10.42 amps. Well, if I look up in my table, I know that we looked at 14 gauge wire can handle 15 amps. In theory, I could put 14 gauge wire in there. But my rule of thumb is never use any wire smaller than 10 gauge. Well, 10 gauge will handle 30 amps. You may find you could get by with 12 gauge for sure. You could even get by with 14 gauge. It'll save you a few dollars, but just bear in mind the cost savings of that little bit of wire, because the difference in cost between 10 gauge and 14 gauge is not that significant. Just in your mind, say minimum 10 gauge, even though we could get by with 14. It's going to save you a world of hurt. Plus, it's going to future-proof. You could add system capacity later. So I'm going to say 10 AWG. So that's what's going to be there. But we only need 10.42 amps here. So then we come into an AC disconnect. Well, in the AC disconnect, there might be a breaker or a fuse. What size fuse? We round up to the next commercially available. It's going to be 15 amps. And then, does anything change when we go through the disconnect? As far as amperage, it doesn't, because all it is just an interruption spot. So from here, we're still going to have 10.42 amps, and we're going to have 10 gauge. Now, what size breaker do we connect into the service panel? That's going to be a 15 amp breaker, because we've rounded up to the next commercially available size. So we would hook in with a 15 amp breaker. So is everybody clear about what we're doing there? Okay. All right. I'm going to clear this screen here. And then I want to talk about the service panel. So if we do a load side connection, which is what it is if we hook in to this breaker in our service panel, and this is the main. Well, there's a thing called the 120% rule about how we can hook up to this panel. So what you'll find is in older homes, the service panel itself has a rating. The little bus bar that all of these breakers connect to, it's a piece of metal in here that all the breakers hook into, has an electrical conductivity or ampacity rating. So let's say that this is 100 amps. The panel is rated for 100 amps. And when we hook in from the utility, we have 100 amp service coming from the grid. We find in older homes, this is very common, where you've got a 100 amp panel and a 100 amp service rating. So what does that mean? Well, at first glance, you might say, okay, well, this panel is full. We can't come in from an inverter with more power because it's already full. But the NEC says you can go to 120% of the bus bar rating, as long as you put the breaker as far away from the main on the panel as is possible. So you don't want to put your breaker up here next to the main. You want to put it all the way down at the bottom. And that's fine. Normally that's where there's open space, if there is open space. And the reason for that is because all these breakers are going out to loads. And what they're figuring is if power is flowing from here and power is flowing from here, it's not going to double up on the bar. So you're not going to exceed that capacity, that 100 amps, because it's not actually going over top of each other. So that's the logic of that. But what is 120%? Well, that means we could come here with a 20 amp breaker. Well, we just in our design said that we needed to come in with 15 amps. So we'll be fine. As far as this design for that size system, we only needed 15 amps. So everything's cool. But what would have happened if we were, say, putting in a, I don't know, a 6 kW inverter? Well, 6 kW, we know that the power coming is 240 volts. So 6,000 watts divided by 240 volts, because watts equals amps times volts, right? So 6,000 divided by 240 gives me 25. Okay, so we're coming out with 25 amps. But we have to multiply that times 1.25. So that gives me 31.25. So if I needed to hook it in here, I would need a 35 amp breaker. Round up to the next available. Well, now we've exceeded the 20%. We couldn't do it. You would not be allowed to hook that in. So what are our options? One option would be to swap out the panel, put a bigger panel in there, put in a 200 amp panel or a 400 amp panel. So that's an option. Now, what if this was already 200 amps with 200 amp service? Well, we could go up to 40 amps and we're fine. We'd just come in with 35 amps. But let's say that it's the 100 amp service. We've exceeded the capacity of this panel. What is an option? Well, one option would be to come from this inverter and connect in somewhere between the service panel and the meter. This is known as a supply side connection or a line side connection. This one down here is known as load side because it's on the load side of the main breaker. This is on the supply side of the main breaker. Okay. So now remember, I said earlier that now the National Electrical Code requires that you put a utility disconnect here at the meter. And because you're installing the solar array, the inspector might say, hey, this is an upgrade of your system, so you got to bring it up to the current code. All right, so that means you've got to put a breaker, a disconnect. Well, usually those disconnects, if you look at them blown up like this, here's the meter. Then there's a double pole breaker here, which basically now becomes your main breaker. But then there's going to be a couple other double pole breaker spots right below it. It's fairly typical. You might have 4 of these right here. Well, if that's what you've done and you've got a problem here with this unit, well, maybe a better place to connect would be right there. It's still a load side connection because now this is your main. So this is a place to connect. So it's load side. You can still install it. The downside with the supply side is this requires an electrician. First off, you'd have to pull the meter. They have to cut into the wire. They've got to put a junction box in there. So it's a bit of a task. If you need to replace the service panel, again, that's a bit of a task. That's going to cost you $2,000, $2,500. If you have to put in and change out the collar and the box here at your meter, well, you're going to have to hire an electrician. But they're going to say, well, you got to bring it up to code, so that's something you got to do. So this is going to be your preferred spot probably to make your connection. And it has a lot of advantages. One is you can size it right off the bat to make sure it's big enough. But also now I don't need to be drilling holes through the wall of my house. I don't need to come into the building itself. I could put everything outside and just connect right up into this. It's especially nice if you're doing microinverters because you've got the inverter up on the roof at the panel. You come down, you go to an AC disconnect, and hook right into the supply. So if I wanted to illustrate that, let's say we've got a house here, and here's all our panels, and each panel has a microinverter attached to it. So now it's generating AC electricity from all these panels. Well, I could even, in a very simple install, use Liquid-Tight and come down the side of the building. So I never even drill into the roof, into the attic of the building. And then I go to an AC disconnect. And it's sitting here right next to the meter. And then if you've got that meter connection, I just go and I connect right here. And that's the whole installation. That's it. Super simple. Nothing is penetrating the building. You might want to, for aesthetic reasons, go through a junction box into the attic and then come out the side so you don't have wires draping over your roof, conduit or whatever. But that's just an aesthetic thing where you go in. This is often a way that we do it when you've got like a cathedral ceiling or something like that, where there's no enclosed attic space. So you've just got to have some part of it exposed. It's not ideal, but it's kind of the limitation you have. Okay, anybody have any questions there? Okay, I think I'll take a look at chapter 9. I'm going to end this. Okay, and see what chapter 9, I think, is batteries. If I remember right. Yeah. And a couple of things to remember with your batteries is the charging process for batteries is different if you've got a lead acid battery versus a lithium ion battery. So lead acid batteries with a pulse width modulation charge controller basically goes through 3 different stages of charge. And the charging is bulk charging. Then there's absorption, and then there's float. So conceptually, the way it works is, let's say that you've got battery bank on your home and you've been using appliances overnight. The sun comes up in the morning and the battery is as low as it's going to be during the day, right? Because you've been running loads all night long. So the battery has been the thing that's been running your loads. And then the sun comes out. Well, what happens? All of the power from your array goes into the batteries to charge the batteries. That's called bulk charging. Your loads are still being run from your battery, but 100% of the power that's coming from the array is going in to charge the batteries. Well, at some point, and it's preset within your charge controller, it starts to slow down. So instead of going full power to full stop when it reaches 100%, let's slow it down a little bit instead of driving like a 16-year-old who just got their license, right? So you're going to start it, and then let's say when you get to 90%, it's set to begin the slow the charging process. How does it do that? Well, it's digital technology. So let's say it's pulsing at a rate of 10 pulses per second. Well, at 90%, it switches to 9 pulses on, 1 pulse off. And then 8 on, 2 off. 7 on, 3 off. So it's modulating the pulse width to slow down the charging process to where eventually it's 9 off, 1 on, and then the battery's completely charged. At which point the charge controller would just stop charging. Now, what happens when the charge controller says, we don't need any more juice? Well, it doesn't hurt the array. The array's just sitting there, out there, fat, dumb, and happy, sitting on your roof. But it's an economic opportunity cost. You know, you might be generating power, but you're not using it. So often in that kind of situation, and this is for a standalone system, you would incorporate a diverted load or a load dump. And it's often going to be your hot water heater. So if I've got more power available, I don't need it to charge my batteries. I don't need it to service my load. I can take that power and use it to heat hot water. Now, that hot water heater is probably not an electric hot water heater. It's probably going to be propane or wood or something like that, because this is a standalone system out in the middle of the boonies. So probably where Jess is right now, right? So who knows? And so you've got, all you're doing is offsetting some other fuel source by using power when it's available, and it's just called load dump. So that's an option. Now that's controlled in your charge controller. But then once you've hit 100%, that's known as absorption mode, when it starts modulating the pulse width. That's why we call these pulse width modulation. Then you go into float mode. Use a little bit of power, replace it. Use a little bit of power, replace it. So I think of it like floating a little boat on the water, right? Goes down a little bit, goes back up, goes down a little bit, goes back up. So those are the 3 stages of a pulse width modulating charge controller: bulk, absorption, float. Now, it used to be in the olden days, we had what we call the series charge controller, and it worked a lot like a thermostat on your furnace. You know, when the power drops below a certain level, it charges. Then it reaches a certain level and it turns off. Then it waits for it to drop to a certain level and it begins charging again. Well, that's not very efficient, because there's long periods of time when your solar array is sitting there doing nothing as you're using power. It's just waiting for it to drop below a certain set point. So pulse width modulation is a lot more efficient than the old series charge controller. Yeah, Jess?
Yeah, I was wondering, I haven't actually gotten to chapter 9 yet because I'm still playing catch up, and this class is hard to speed run.
Yeah.
But I was wondering if you cover the lithium iron phosphate batteries that are, I think they've really taken over like the lithium ion space even, because that's what I have. We used to run, you know, these lead acid batteries, and we very happily dumped them once the beta phase of the lithium iron phosphates were done with, and we honestly couldn't be happier with them. They're low maintenance. You don't have to do anything. In fact, you shouldn't do anything to them.
Yeah, the nice thing about the lithium ion is typically the battery management system is built into the battery itself.
Yes.
So you don't need a charge controller. It's basically controlled within the unit. If you crack it open, you'll find electronic devices inside there managing that system, because they are temperature sensitive. There's a lot of stuff that they have to do in the management, so they're just integrated in. They use a different charging process, and that charging process is referred to as constant current, constant voltage. And what that does is basically, when you hook it up to a charger, 100% of the current goes in to charge the battery. So it's like bulk charging, right? Whatever
Charge
you're doing,
fast. Yeah.
it's just charging. Yeah. And then it reaches the set voltage, because as you're charging, the voltage will go up. And at some point it reaches like its operating voltage, but it's not 100% full yet, even though it's reached that operating voltage. It takes a while. So it keeps the voltage constant, but begins to diminish the amount of amps that are coming in. So at first it's 100% of the amps and the voltage is increasing. Then it hits voltage and the voltage stays the same, but the amps start to decrease. And so that's just referred to as constant current, constant voltage. So it requires a different charging process. This comes into play a lot with electric vehicles, because one of the concerns people have around electric vehicles is, you know, my gosh, it takes 10 hours for this thing to fully charge. I don't want to take it on a cross-country trip and I got to stop at a gas station and charge this thing for 10 hours. What am I going to do? So what you find with these high capacity chargers, the level 3 chargers, is you can charge it in that constant current portion, and that'll take it to about an 80% state of charge. And some of these fast chargers will do that in 5 or 10 minutes. So you could pull in with your Tesla or whatever, charge for 5 to 10 minutes, and it's 80% charged. That last 20% might take you 10 hours to get the last 20%. Well, I don't need it. I'm going to drive to my Aunt Bertha's in California. So it's like filling up your tank to 80% rather than chock a block full. Well, okay. It doesn't damage anything. It doesn't cause any problems, but it's a lot faster. I can get 80% in 10 minutes. And then when I get home, yeah, I'll charge it overnight and it'll get 100% full. But so you can take advantage of that constant current, constant voltage where 80% state of charge. And if your car has a 400-mile range when it's full, well, now it's got 320 miles till you need to stop and charge it again. So that's how they're getting past the range anxiety thing, or the amount of time it takes to charge. Is you just don't charge it all the way. You only charge it to that set point.
But is there a difference between like the battery that I got for my house? It's a lithium iron phosphate. Is there a difference between that and like the lithium ion car batteries? Because my impression is there is a difference kind of in their chemistry and also in their kind of thermal properties.
Yeah, there are probably 6 or 8 different flavors of lithium ion batteries. The advantage, I think, and I'll probably get it wrong, but I think it's the lithium iron phosphate, is less prone to thermal runaway. They're a little bit more robust. And that's one of the reasons they like them in homes. But they're also, some vehicles are using them. So sometimes it's going to be the same as that.
Okay.
So there are different advantages and disadvantages of each battery chemistry. Some are less expensive, some are more expensive, some are less prone to thermal runaway, some charge faster. So each one has its advantage and its disadvantage. That's why we haven't settled on just one battery chemistry. But
yeah, I know my batteries won't go 0 to 60 in 5 seconds, but I don't need them to because they're powering my fridge.
Yeah, that might be another advantage of a certain type, is it will allow you to discharge quickly without losing a lot of its capacity. Because typically with a battery, the faster you're discharging, the less capacity it has. So you might have a 100 amp hour battery if it's discharged over 100 hours. But if you discharge the whole amount in 1 hour, it might only have 22 amp hours of capacity.
Mm-hmm.
So that's a big issue. Yeah, we're still, I always like to say we're in the floppy disk age of solar, but we're in the ticker tape punch card age of batteries. We're just at the very beginning. These things are just becoming viable as a technology. So I guess the battery you just installed, I would make the analogy of you just bought like a 1984 Mac. It's cool, it's state of the art, but
those things run forever.
Things are going to change.
Yeah.
Things are going to change. So, yeah, I bought a 1984 Mac and I paid $3,500 for it in 1984, and it had 128K of processing power and 2 floppy disks. Each one held 400K. So, man, it was really state of the art. Now, anybody's watch is smarter than that thing. So, all right. So that sort of covers some of the items in the battery thing a little bit. Anything from past chapters that you are feeling a little bit insecure about or a little confused? Nope. I know as you mentioned there, Jess, it's a lot of information to absorb. I don't think that there's any part of it that's super complicated. It's just that you're absorbing a lot of it in a fairly short period of time. So,
yeah, I know I had to take the Pathfinder quiz like 3 times before I passed it. That one drove me nuts. My one
Yeah.
question was like it's on a grid and like each horizontal, well, curved but horizontal line is a month. Now, do
Yeah.
you read like the percentage of light because it gives you the little numbers? Do you read just on that line or do you read the whole box as being the month? Because I was just getting the numbers totally wrong because I was
Yeah.
reading the box, I think. And when I started just reading the line, I eventually managed to pass that quiz.
Yeah, it should be 100% just on each level. Yeah, that part of it is it's diving into the weeds a lot. Mostly you're just sort of looking at it going, is this a good spot or is it not? You know, you don't need typically to figure out what percentage of shading. I only brought that up because I
Yeah.
wanted to show that it does exist. You have that capacity. So Rich just asked about voltage drop. So let me run through a real quick voltage drop question and then we'll call it a day here. So what is voltage drop? Well, if we have our system here, typically the portion where voltage drop comes into play is between the junction box or the combiner box and the DC disconnect. That might be on a roof and that's going all the way down. All the other distances are going to be short, only 5 or 10 feet. So this is the one that's long. So if this were a standalone ray out in the middle of a field somewhere, and let's say the distance. So we look at the distance and it's 285 feet all the way from here to here. So the question is, how much voltage are we going to lose? Well, so we've got a few formulas we have to remember. One of those formulas is watts equals amps times volts, right? This is the power equation. Watts equals amps times volts. If you don't have that in your mind, you're going to be in trouble. Okay, then there's Ohm's law, which is volts equals amps times resistance. So that I just think of Ver, right? All that these are doing is telling you there's a relationship between these things. If you know two of them, you can figure out the third one. And we get some things like Ohm's law triangle, where volts over amps times resistance. So if I want to figure out volts, I do amps times resistance. If I want to figure out amps, I do volts divided by resistance. It's V over R. So it's just a way you can do all of these math problems without really knowing algebra. So it's a visual way of if you just set up that triangle. So what is voltage drop? Well, this is the third equation you need to know. Voltage drop equals amps times resistance times twice the distance divided by 1,000 feet. Well, if you look at it, it's really just Ohm's law, but it's adjusted for distance. Why is it adjusted for distance? Is because the resistance we're given for wires out of the NEC is in ohms per 1,000 feet. So I need to know what portion of 1,000 feet, and it's twice the distance because it's a circuit. The wire goes there, it goes back. So all I'm doing is, because I'm given resistance in terms of ohms per 1,000 feet, I'm adjusting it for my distance of the run. So if, let's say, my amps, and in this case I'm going to use IMP, so we often just put IMP here because the ohms, the current of one panel is going to be the current of the string. So if I've got a string here, and let's say I've got an IMP like in the last one of 9.3 amps, well, now I've got 9.3 amps. I know that here. What's the resistance? Well, I don't know that yet, but I do know twice the distance. 2 times 285 is going to be 570. Is that right? So 570 divided by 1,000 feet. Well, that's easy. Just 0.57, right? So I have 9.3 times whatever the resistance is times 0.57. So if I'm using number 10 wire, I know that the resistance, we can look it up in the table, but I happen to know it's 1.24 ohms. So now I've got all my factors, so I can figure out my voltage drop. Well, I just take 9.3 amps times 1.24 ohms times 0.57, and I'm going to lose 6.57 volts. 0.57. Well, is that acceptable? We want to keep our voltage drop somewhere around 2%, certainly no more than 5%. Well, I don't know. Is that acceptable? Well, if it's a 12-volt system, I just lost more than half of my power. Certainly not acceptable. Well, in our previous example, we said that the IMP was 27 volts, and I said that was 10, so it's 270 volts because we hooked them up in a string. Well, 270, so I've got 6.57 volts divided by 270 volts, and that gives me a little over 2%, I think, right? 6.57 times, or sorry, 6.57 divided by 270. Yeah, 2.43%. Well, is that acceptable for voltage drop? It basically means from here to here, I'm going to lose 2.43% of my power. Okay, I'm going to lose 6.5 volts. That's 2.43% of my power. I could probably live with that. We're going to lose something. So what's my options? Well, I could shorten the distance. I could make this thing closer, but I probably put this thing here for a reason, and hopefully it was a good reason. So maybe that's the only place it can go. I could increase the voltage of my system, or yeah, as Rich just said, bigger wire. And that's normally what we would do. So instead of 10 gauge wire, I might put in 8 gauge wire. And then I'd have to look it up because I don't have 8 gauge wire memorized. But I think it's here in page 90 something. Yep, here we are, page 92. 8 gauge wire. Yeah, 0.778. So now my equation is all going to be the same, except it's now 0.778 ohms. So 9.3 times 0.778 times 0.57. So now it's just 4.1 volts. And it's still going to be 270 volts. So I brought the number down below 2%. Now, when we do the voltage drop, in theory, I'm supposed to calculate voltage drop for this, voltage drop for that, voltage drop between the DC disconnect and the inverter, between the inverter and the AC, between the AC and the service panel. You know, you can do all that, but that's a lot of calculations, and it usually doesn't add more than just a wee little bit. It's usually just this PV output circuit, the one from the combiner box or the junction box to the DC disconnect. That's the one with all the distance. So that's the one we normally focus on. And if you've left yourself a little bit of slough, you're all right. You know, but bigger wire is usually the system. Another thing you can do, increase the voltage. So if I had 2 strings and they were 270, if I could get one string that was closer to 600, well, I've just reduced my voltage drop, because if the system were 600 volts and it was still 6.5, now we're just over a little bit over 1%. So mainly the things we do, reduce the distance, increase the size of the wire, or increase the voltage of the system. Those are usually our things that we can combat voltage drop. All right, so that covers voltage drop. Hopefully that helps you out there, Rich. I see it's Rich A, but I'm assuming it's Rich, or is it Richard, or whatever. I know your mic's not working, right? All right. Rich is fine. Okay, great. All right. So that covers us for today. And we'll meet again next Tuesday. That'll be our last session before we get together then on the 22nd and 23rd. Okay. All right. See y'all later. Bye bye.